Hey everyone, and welcome to this explainer. Today, we are setting off on a seriously incredible journey into the hidden yet absolutely fundamental world of cutting-edge materials. I am so thrilled to guide you through this because we're going to look at metallurgy in a way you've probably never seen before. We are moving far past that traditional image of blacksmiths and molten steel and diving right into the absolute bleeding edge of modern science. So think about this for a second. What do microscopic phone chips and massive jet engines actually have in common? Literally on the surface? Absolutely nothing, right? One fits on the tip of your finger, processes your entire digital life, and operates in total silence. The other weighs tons, roars with fire, and propels hundreds of people through the sky. But I'll let you in on a secret. The answer to this wild comparison lies entirely in how we manipulate metals at the most fundamental level. Okay, let's dive into this. Here's our roadmap for our zoom-in, zoom-out journey today. First up, the metallurgy of extremes. Then, we'll look at semiconductors, the nano world. After that, aerospace, the macro world. And we'll wrap it all up with two extremes, one future.
All right, part one, the metallurgy of extremes.
You know, there's this fascinating paradox we're exploring today. It's the delicate, precise needs of microelectronics up against the brutal, explosive demands of aerospace. But there is a hidden thread connecting these two vastly different worlds. Modern metallurgy is no longer just melting things in massive crucibles and crossing our fingers for good results. Today, whether you're building a tiny microchip or a giant turbine blade, the shared foundation is atomic-scale precision and computational prediction. We are literally designing materials virtually before they ever exist in the physical world, and we're constructing them with a level of control that honestly borders on science fiction. Moving right along to part two, semiconductors, the nano world.
We are zooming way into the microscopic scale of semiconductor fabrication, where real estate is basically non-existent. Down here, space is tight and precision is everything. And the big bad villain? Electromigration. This is the failure of nanowire interconnects when subjected to high current densities. What does that actually mean for you and me? It means your electronics literally frying from the inside out. As we pump more power through tinier and tinier copper wires on a chip, the actual physical momentum of the electrons pushes the metal atoms out of place. It's kind of like rushing water eroding a riverbank. This causes voids, short circuits, and eventually total failure. This interface diffusion is exactly why we desperately need highly engineered nanoalloys to lock everything securely into place.
So how on earth do we build these protective nanoalloys? Well, enter Co-ALD, which stands for Atomic Layer Co-Deposition. We aren't melting metals down here. Instead, we're synthesizing alloys directly onto the silicon wafer using sequential, self-limiting gas surface reactions. Let me break that down. Think of it like laying down a perfect molecular brick wall. You introduce a specific gas, it reacts with the surface, and it lays exactly one perfectly flat layer of metal atoms, let's say cobalt. Then, you clear the chamber out, introduce a completely different gas, and it lays another perfectly flat atomic layer, maybe tungsten. You are chemically building an alloy, like cobalt tungsten, entirely from the bottom up.
And the sheer scale of this breakthrough is just staggering. One atom, that is the exact thickness at which engineers can now control the chemical composition of an alloy. When you're coding complex three-dimensional transistor architectures, any tiny gap or uneven pooling of metal is totally catastrophic. By controlling the synthesis down to the precise thickness of a single atom, we ensure a perfectly uniform film distribution across microscopic canyons and ridges, completely avoiding those dreaded voids.
Now, what's really interesting here is another physical vapor deposition technique called HiPIMS. That's high-power impulse magnetron sputtering. It utilizes extremely high power densities and incredibly short pulses to ionize a massive percentage of metal atoms. Imagine firing a highly energetic, electrically charged stream of metal atoms straight down into deep, incredibly narrow microscopic trenches on a wafer. Because they're ionized, they can be magnetically directed right to the bottom of the trench. This highly ionized metal flux creates ultra-dense, highly adherent barrier layers that stop that electromigration we talked about right in its tracks.
All right, let's violently zoom back out. Part 3, Aerospace, the macro world.
Shifting from the nanometer all the way up to the meter scale, we enter the high-heat, extreme stress environment of jet engine turbines. Up here, the enemy isn't electromigration, it's thermal creep. This is the dangerous deformation of structural materials under prolonged exposure to high temperatures. Imagine a turbine blade spinning thousands of times a minute inside a literal inferno, operating just below its melting point. Over time, under that extreme heat and massive centrifugal stress, the metal actually stretches and deforms. If it creeps even a fraction of a millimeter too much, it strikes the engine casing, and boom, catastrophic engine failure. This terrifying failure mode is exactly why materials scientists are on a relentless hunt for superalloys that exhibit zero creep.
And here's how they're synthesizing them today: directed energy deposition, or DED. This is dynamic 3D printing, but unlike any 3D printing you've ever seen. Instead of plastic, we're using gradient elemental powder flows. Picture a high-tech DJ mixing records, but instead of audio tracks, they have multiple powder feeders injecting pure elemental metals, like nickel, chromium, cobalt, rhenium, straight into a high-powered laser beam. By dynamically changing the mix of those powders on the fly, a single printed component can feature a gradient alloy composition. So you can print a part that has a tough, ductile core to resist cracking. It seamlessly transitions into a highly heat-resistant superalloy on the outer skin. It's brilliant.
But hold on. Before we fire up the lasers, how do we know which elements to actually mix? Billions. That staggering number represents how many potential elemental combinations advanced AI models analyze before we physically melt a single ounce of metal. Traditionally, discovering a new superalloy took decades of physically mixing, casting, and breaking test pieces. Now, we just simulate the whole shebang.
Let's walk through this incredible integrated computational materials engineering process. Step 1, AI systems, using tools like CowPad, predict phase stability and simulate how atoms will interact across those billions of combinations. Step 2, out of the digital ether, an optimal recipe for a high-entropy alloy or a single crystal nickel superalloy is identified. Step 3, once we have that perfect digital blueprint, we physically synthesize it using vacuum induction melting, or VIM. By melting the metal in a complete vacuum, we eliminate interstitial impurities, like oxygen or nitrogen, that would otherwise weaken the metal. This pipeline, straight from computational prediction to vacuum synthesis, dramatically reduces the trial and error cycle, bringing these zero-creep materials to life faster than ever before.
And that brings us to part 4, 2 extremes, 1 future.
And this brilliantly illustrates everything we've mapped out today. We've traveled from the invisible landscapes of silicon wafers to the fiery belly of jet engines. And the dichotomy of these two fields is stark. I mean, the scale is drastically different. Nanometer-thin films versus massive meter-scale bulk components. The technologies are entirely distinct, right? Gas reactions and ionized sputtering for chips versus dynamic laser powder synthesis and vacuum melting for jets. They combat totally different enemies, too. Electromigration versus thermal creep. But look at the bigger picture. Both rely on an uncompromising mastery of chemistry and physics, uniting around the power of artificial intelligence to design and atomic-level precision to actually execute. So the crucial takeaway here is that we are no longer constrained by the materials we simply find in the Earth. We are actively inventing flawless, customized materials, atom by atom, tailored for the absolute most extreme environments imaginable. Which brings us to this final thought. What is the next frontier for AI and atomic synthesis? If computational engineering and absolute precision can prevent microscopic short circuits and stop jet engines from tearing themselves apart today, just imagine the impossible technologies these materials will enable tomorrow. Keep asking questions, and I will see you in the next explainer.